Hi, this is Professor Bob Young, and I'm going to begin a college trigonometry course with this being the initial first video, and I'm going to try to teach the course in its entirety to the last video, and this will no doubt take some time on my part, but I have a lot of students after me to do it, so here we go. The first video is entitled, we're going to do some basics of trigonometry here, talking about angles in radian and degree measure. So the objectives for this first video is to recognize and use the vocabulary of angles, looking at the first bullet. Use degree and radian measure, convert between the two. We're going to draw some angles in what's called standard position. We're going to define coterminal angles and see how those work as well, and probably draw some of those. Find the length of a circular arc, and we're going to do some physics here. Those of you in physics courses, we're going to use linear and angular speed and look at those formulas to describe motion on a circular path. All right, angles are formed by two rays that have a common endpoint, and in this case, the endpoint is called the vertex, and this is point B. One ray is called the initial side, so that's where the angle begins, and the other ray is called the terminal side, where the angle ends or terminates. And notice there is an angle in here called theta, and they like to use lots of Greek letters when they name these angles, and we'll discuss those as we go along. Now, an angle in what's called standard position is when the vertex is at the origin here, the point 0, 0, and in the rectangular coordinate system, and its initial side lies along the positive x-axis. So here they have angle alpha here, so the positive x-axis will be the initial side when we're in standard position. And here's an angle here, it's called theta. When we see an initial side and a terminal side in place, there are two types of rotations that could generate the angle. Now, if the angle is going counterclockwise, it is considered to be a positive direction. And if it's going clockwise from the initial side, it is considered a negative direction. All right, now an angle is called a quadrant angle if its terminal side lies on the x or the y axis. So in this illustration, angle beta is an example of a quadrant angle here. And we're going to learn that each quadrant here, like if the angle was here, it would be 90 degrees. This would be quadrant 1, quadrant 2, 3, and 4. So when that terminal side lies on the x or y axis, these are going to be some very important angles as we progress. All right, now here's some angles that you may remember from high school geometry courses and so forth, some definitions here. An acute angle is an angle that's less than 90 degrees. A right angle measures 90 degrees. An obtuse angle is between 90 degrees and 180. And a straight angle is a 180 degree angle. And if you think about it, that could be two right angles combined if you put a perpendicular right up and down through here. All right, so we want to go ahead and look at the quadrant angles in degrees. And I want to talk about what's called the unit circle here, along with some points on it here. Right now, a unit circle has a radius of 1. So if we went from the origin here out, this would be the point 1, 0 on the x and y axis. So if you want to, we can label this x and y here. This point up here would be 0, 1, x would be 0, y would be 1, negative 1, 0, and 0, negative 1. So these x and y values are going to become more and more important as time goes on as well. All right, now if we start at the positive x-axis here, so we call this the initial side, and we rotate around, we can see that really we have four right angles here. So we're going to have this first angle would be 90 degrees, and just adding 90 all the way around, we would get, of course, the straight angle would be 180 degrees. We just talked about that. Another 90 would give us 270, and a full rotation of a circle then would be 360. So really you'd have four right angles in here. All right, now we want to go ahead next and look at degree measures using these quadrant angles, and I'm going to call this 45-degree increments. So we've already gone all the way around. So now we're going to cut these 90-degree angles in half, and we're going to see what happens. So if we go half of 90, right in the middle here, we would get a 45-degree angle. And of course, if we keep adding 45, we'll get 90. Another 45 will give us 135. So what we're doing is just like cutting this circle in half. And then of course, another 45, we're back to our straight angle 180. Plus 45, we're down here. This is quadrant 3 now, and 225 degrees. 270 degrees, and we are going to find that these are very friendly unit circle angles as we progress. 315 degrees and then back to 360. So what we're doing here is we're just adding 45 degrees as we progress along here. And we can also go a negative direction if you want to think about it here. If we were to go in this direction, we would have a negative 45 degrees, negative 90 degrees, and so forth. We could go the negative direction all the way around as well. Let's go ahead and take the circle and break it into 30-degree increments here. So instead of breaking it half and half here, we're going to go in terms of 30 degrees around the circle. And again, we're going to use the quadrant angles as we do this. So these are very important angles to identify as you begin your trigonometric adventure. All right, so let's go ahead and identify, we'll call this 30 degrees. So all we're going to do all the way around the circle is we're going to break it up a little differently here in terms of 30 degrees now. So we're going to go 30, 60, 90. And if you just keep adding 30 degrees around here, look how quickly you can get around. And all of these angles are going to become, again, extremely important as time progresses here. So these are the ones you want to kind of get a really good feel of. You want to know, for example, what quadrant 300 degrees is in and so forth. And notice if I just keep adding 30 all the way around here, if we break this thing into sixes, basically is what we're doing here. 1, 2, 3, 4, 5, 6. So a half of a circle is breaking it into sixes. We're just going to add 30 degrees around. Now, again, if we went negative, if we went the negative side, yes, Young, you could do this all the way around. Now, I'm not going to go all the way around again, but I hope you're starting to get the picture here. All right, now, angles are not only measured in degrees. The more calculus side of this is they talk about what's called a radian measure. In calculus, most angles and trig that you see will be in radians rather than in degrees. So this is very important. And let's look at how this compares to degrees here. Now, 1 radian is the measure of the central angle here of a circle that intercepts an arc equal in length to the radius of the circle. So if I took this radius of a circle here, and of course that starts from the center and goes to the outside of the circle, and bended it around, when that arc length is equal to the radius, this is considered 1 radian. All right, so if I went ahead and I took a circle over here, and what I did is I want to show you how to break it into radians here on the side. So let's look at this. So if this is the radius and we go ahead and make equal lengths around here, I'm just ballparking this. This would be about 1 radian. Let's say about 2 radians here. 3. And we'll just keep going here. 4, and these should be nice and even. I'm sorry if I'm messing them up just a little bit. 5 and 6 and a little bit left over there. So there are really about 6 radians all the way around a circle here. And if you think about if this were a unit circle, if this was r equals 1, this circumference formula, which is the outside perimeter basically of a circle, would be c equals 2 times pi times 1, so the circumference would be 2 pi. So in degrees, we went around the circle, it was 0 to 360 degrees. In radians, it's 0 all the way around to 2 pi. And if you think about it, 1, 2, 3, if this was 2 pi, this half of this would be 1 pi. which is about 3.14. So you'd have 1, 2, 3, and a little more would be about 3.14. And we're going to see how this works as we continue. So if we're going to look at the quadrant angles and radians, remember these were 90 degrees, 180, 270, 360. Remember, if we start at 0 radians and we go all the way around to 2 pi, which again is just a number here. That was the circumference if we went all the way around. Let's think about this. Well, half of 2 pi would be 1 pi radian over here. That's kind of a bad pi. And then if you took half of pi, this would be pi over 2 radians. And if you added another pi to pi over 2 to pi here down here, this would be 3 pi over 2 radians. So these are very important quadrant angles here. And notice that some of these things match up, like pi over 2 matches up with 90 degrees, pi matches up with 180, and so forth and so on. So we'll go ahead and keep looking at those as we continue. All right, so like I did with degrees, I want to do the same thing with radians now. So what we said we had was pi over 2 pi, 3 pi over 2, back to 2 pi here and starting at 0. Now, if you think about this, if we want to break this thing up into pi over 4 increments or 4s, like we did when we had degrees, we broke it into 45 degrees. Check this out. Half of pi over 2 is pi over 4. So what I like to do is just add pi over 4 all the way around to get these angles in radians, because you're going to have to recognize these common trig angles as we progress in the course. So let's go ahead and do this. I'm starting at 0. Y'all ready? Here we go. 1 pi over 4, 2 pi over 4. Hey, that reduces to pi over 2. Check that out. 2 pi over 4. So you always use the quadrant angles as you are getting these common radian measures. 3 pi over 4, I'm just adding pi over 4. 4 pi over 4 is pi. 5 pi over 4. 6 pi over 4. 7 pi over 4. Notice 6 pi over 4 reduces to 3 pi over 2. And then look at this, 8 pi over 4, we're back around. So a lot of times students have trouble recognizing these common radian angles here. So I'm going to go ahead, and you could also go negative on these. Negative pi over 4, negative 2 pi over 4, negative 3 pi over 4, all the way back around to negative 2 pi as you wanted to. And we're also going to do it in terms of 30 degrees, and we're going to call in 6s. So I call this the 4s here. We bust it up into 4s. 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, all the way around to 8 pi over 4. Okay, now here we go again. If this was 30 degrees, if we broke this up, and I'm going to call this the 6s. Break it up into 6 parts, 1, 2, 3, 4, 5, 6, half the circle here. This 30-degree angle would be 1 pi over 6. 2 pi over 6 would be pi over 3. So this is 2 pi over 6. Notice, hey, 3 pi over 6 is here, pi over 2. 4 pi over 6 reduces to 2 pi over 3 radians. 5 pi over 6, 6 pi over 6, 7 pi over 6. So I'm really just adding pi over 6 all the way around here. 8 pi over 6 reduces to 4 pi over 3. You have to kind of be good at fractions when you do trig. 9 pi over 6 reduces to 3 pi over 2. 10 pi over 6 reduces to 5 pi over 3. 11 pi over 6 back to 12 pi over 6, or 2 pi. And of course, you could go negative as well. And again, become very familiar with these, and we're going to get to these triangles and where this comes from as we progress as well. So ladies and gentlemen, I present to you degree and radian measures of angles commonly seen in trigonometry here. So from the initial positive x-axis side, this is going in a positive direction. I've got both degrees and radians as we have talked about them all the way around, positive and negative here. These are the things you must begin to learn as we progress. All right, now there is a relationship between degrees and radians. So if you're better in one than the other or vice versa, you can become really good in both. Now remember, using the basic relationship that pi radians equals 180 degrees, we talked about that earlier in the video. Here's some formulas here to convert from degrees and radians to radians, excuse me. Multiply degrees by pi radians over 180 degrees. 2, to convert radians to degrees, multiply radians by 180 degrees over pi radians. And we're going to go ahead and take some looks at examples of those here. So here's some examples we're going to go ahead and look at. So to convert 60 degrees to radians, just multiply by pi radians over 180 degrees. And what I like to do, they went ahead and showed this step. I like to chop whenever I multiply fractions. I like to put a 1 under this and say 60 goes into 180 3 times. The degree units also cancel out, leaving you with pi over 3 radians. So in class, I'll get kind of corny and go, ooh, we want to become black belts whenever we do that. All right, multiplying 270 degrees, changing degrees to radians by pi radians over 180. I think everyone will see 90 goes into 270 3 times, and 90 goes into 180 2 times. The degrees cancel out, leaving you with 3 pi over 2 radians. And if you go back, you can see that on the circle that we had, these two match up. Ooh, they slipped a negative one on us here, Young. So if you go negative 300 degrees times pi radians over 180, do y'all see what number goes into 300 and 180 here? I think it's going to be 60. So that would be a negative 5. 60 goes into 183. And of course, you could write it like this and reduce the fraction this way. As long as you get to the bottom line over here, we are happy. All right, converting from radians to degrees now, we're going to go ahead and do the same thing, but flip the fraction here. So pi over 4 radians, if you wanted to show the units, times 180 degrees over pi radians. Check this out. The pi radians, the radian units cancel out along with the pi's. And then 180 over 4, you could chop 4 into 180, you will get 45 degrees as pi over 4 radians. And similarly on the other ones, negative 4 pi over 3 radians times 180 degrees over pi radians. Let me tell you what, these will be on the test. Converting from degrees to radians and vice versa, very important. All right, equals, and they kind of wrote it like this, negative 4 times 180. Then you could say, well, 3 goes into 180 60 times and do a mini chop there. And then 60 times 4 would give you negative 240. And then they just gave you a negative 6 radians here. And then multiply that by 180 degrees over pi radians. The radians go out here. Oh, look at that. We don't have any chop in here. We've got 6 times 180 degrees over pi. So we'll use our calculator here and divide this by pi. And it's going to be approximately, and sometimes you have to do this if it doesn't go in there exactly, approximately 343.8 degrees. So just some examples of converting from degrees to radians and vice versa. All right, now that we're starting to get the feel for some of these angles, the ones that we know and love, let's go ahead and sketch some ones that are not so apparent here. Starting with theta is 70 degrees. Now, if we know that this starts at 0 degrees or 0 radians, and this goes to 90 degrees, I would say a good sketch of where we need to go would be right in this first quadrant here. So I would go ahead and label this theta here as a ballpark figure. Now, doesn't have to be super perfect. Where would 250 degrees lie? So getting to know these angles, 90, 180, well, 270s here, Young. So we passed 250. So it's 20 degrees inside of 270. So I would say that angle theta would lie in quadrant number 3. 400, let's see what happens. 90, 180, 273. Oh, Young, you passed 360. How'd you do that? And then another 45 would be halfway. So 400, I'm going to say, is just inside that 45 degrees. Now notice on this one, if I start and I draw this angle, I have to go past 360 and loop back. So I'd have to go from 0 to 360, plus another 40. So make sure that you show these correct rotations here. Negative angle, 190, you'd go the opposite direction, negative 90, negative 180, a little bit past negative 180. Here, I'm going to go another 10 degrees and try to slice that a little bit from that positive x-axis. Call that theta. So make sure you can start getting the feel for where these angles end up, what quadrants and so forth. And now radian, students have a little bit more trouble here. But let me try to give you a way to show you how to do this. If you know this is pi over 2, it's also 5 pi over 10. And if you want to graph the angle pi over 10, you'd have to try to break this part right here into fifths or into tenths, and it would be really 5 pi over 10 would be here. So this would really be 1 pi over 10 in the first quadrant. So we could put theta there. And then you go 2, 3, 4, 5 pi over 10 would be there. So it would really be wrapping this around in tenths. 7 pi over 8. Think about this one. Pi over 2 in terms of 8 would be 4 pi over 8. Okay, pi would be 8 pi over 8. So 7 pi over 8, if you're thinking about breaking this up into eighths, would be pretty much closer, I would think, to 8 pi over 8. Maybe not exactly right there, but again, getting a feel for it, close enough here. All right, 17 pi over 4. Now look at this one. If you're thinking pi over 4, we know that that's halfway here. This one, 4 goes into 17 4 times. So you would get 4 pi plus another pi over 4. Or you could think of 4 pi as 16 pi over 4 plus pi over 4, 17 pi over 4. So check this out. I'm going to go around 1, 2, 3, 4 pi to pi over 4. And here's how you would sketch this one. You'd start at this positive x-axis and you would go 1 pi, 2 pi, 3 pi, 4 pi, and then stop there. So notice that 17 pi over 4 and pi over 4 are going to be what we're going to call later coterminal angles. They have the same terminal side. All right, so, and if you start thinking about other things we talked about, this is getting interesting. All right, negative 3 pi over 2 would be negative pi over 2. Negative pi would be back around here. So we are just getting the feel for some of these angles. Be sure you can sketch them as well. All right, we're going to look at what's called coterminal angles here. Two angles with the same initial and terminal sides, but possibly different rotations are called coterminal angles. So what I like to say is coterminal angles have the same terminal side. So we'll look at an example in degrees and one in radians here. So if you go adding or subtracting 360 degrees, and you can, this K number, you can do it as many times as you want. So if this is 60 degrees, you could add 360, add 360, add 360. The K number, you could go K is 1, 2, 3, 4, 5, and to infinity, or -1, -2. But if we add 360 degrees to this, we'll have a 420 degree angle. So it would just wrap all the way around and stop. These are called coterminal. They have the same ending side. And if you took that 60 degrees and subtracted 360, you would be at a -300 degrees, wrapping back around this way. All right, so there are infinitely many coterminal angles to a given angle in trig. And in radians, 3 pi over 4, well, again, instead of adding 360, we're going to add or subtract 2 pi here. So if we added another 2 pi and we did this creature, wrapping back around to get to the same terminal side. Now remember, you can go ahead and make that into fractions here. So 2 pi, we get a common denominator of 4 here, would be 8 pi over 4 and 3 pi over 4. So you get 11 pi over 4 radians as a coterminal angle. And of course, you could subtract 2 pi from that 3 pi over 4 and get -5 pi over 4 radians. So coterminal angles, huge as we progress. All right, a few more examples on finding coterminal angles here. We'll take a 400-degree angle, and it says, assume the following angles are in standard position. It says, find a positive angle less than 360 degrees that is coterminal with each of the following. So if you said 400 degrees here, you'd have to, instead of adding 360, you'd have to subtract 360 to stay within the parameter of the problem. You'd get 40 degrees. A negative 135, you'd have to add 360 for a positive angle that's less than 360 to get 225. So when you start doing your assignments and so forth, watch out for the directions. Again, it says assume these in radians are in standard position. Find a positive angle less than 2 pi that is coterminal with each of the following. So 13 pi over 5, if you subtract 2 pi, notice they made a common denominator there of 5 with 2 pi. They got 3 pi over 5 radians. Negative pi over 15, they added 2 pi, got a common denominator of 15, put a 1 under the 2 pi there, and got 29 pi over 15, which is just less than 2 pi, isn't it? Because 30 pi over 15 would be 2 pi, so interesting there. All right, we're going to discuss next measuring angles using radians here. And we've been talking about unit circles with a radius of 1, but this really extends far beyond that. So the beauty of trigonometry here, an angle whose vertex is at the center of a circle is called a central angle. And we've been talking about those and graphing those and so forth. A radian measure of any central angle of the circle is the length of the intercepted arc divided by the circle's radius. All right, so we've got a picture here, and it says consider an arc of length s, so they call s arc length here, on a circle of radius r here. We can get this central angle in radians simply by taking that arc length and dividing by the radius. So we'll go ahead and look at an example of that here. So it says a central angle theta in a circle of radius 12 feet intercepts an arc of length 42 feet. What is the radian measure of theta? So the arc length 42 divided by r here, 42 over 12, would be about 3.5 radians. And if you think about where this would be on the graph, 3.5 radians, and again, I just etched a circle out here with a radius of r, and I took this arc length here and I called it r as well, be 1, 2, 3 radians. Now remember, pi is about 3.14, so this actually makes sense. All right, 4, 5, 6, 2 pi would be about 6.28. So 1, 2, 3, 3.5 would be about this angle right in here if we were going to go ahead and measure that on the graph. So just trying to keep those angles familiar. All right, now this brings us to our next big topic here. It says the length of a circular arc. It says r, let r be the radius of a circle and theta, the non-negative radian measure of a central angle of a circle. So the length of the arc intercepted by the central angle is s equals r times theta. And you can probably see where this formula came from based on our prior discussions, because they just really took that formula theta equals s over r and multiplied both sides by r here. So what we're trying to establish, there is a definite relationship between these three things: the central angle in radians, the length of this radius, and the length of this arc. All right, so it says finding the length of a circular arc here. We'll do an example. It says a circle has a radius of 6 inches. Find the length of the arc intercepted by the central angle of 45 degrees. Express arc length in terms of pi, then round your answer 2 decimal places. So notice in this formula s equals r theta we've been talking about, theta must be an angle in radians. And what did those people do to us? They gave us degrees, so that's easy enough. We'll just take 45 degrees times pi radians over 180, get pi over 4 radians, and then take the radius times that angle, and we'll get approximately 4.71 inches there for our answer, the arc length S. All right, the last few examples, we're going to talk about definitions of linear and angular speed here. So it says if a point is in motion on a circle of radius r through an angle theta radians in time t, then its linear speed v here is given by s over t. Now remember again, the arc length s is r times theta here. So we've learned that formula here. And it says where S is the arc length given by, of course, what I just said there, S equals r theta. And its angular speed is W equals theta over t. Now, of course, these are Greek letters and so forth here. And W is called omega in Greek, all right? So the linear speed v of a point of a distance r from the center of rotation is given by linear speed equals r times w, or r omega, where omega is the angular speed in radians per unit of time. I know that may not have bounced off of people well, so we'll look at an example and I think it'll make more sense. So here we go. Long before iPods that holds thousands of songs and play them with superb audio quality, individual songs were delivered on 75 RPM and 45 RPM circular records. So maybe your parents or grandparents, or even you, have some of those old vinyl records. So we'll use one of these as a reference point. A 45 RPM record has an angular speed of 45 revolutions per minute. Now, I don't know if y'all knew that when you were playing those old discs, but that's what's happening. Find the linear speed in inches per minute at the point where the needle is 1.5 inches from the record center. Okay, so what we're going to do is we're going to apply the formula linear speed equals RW. Now, before we can do this, once again, we have to get omega here in terms of radians per second. All right, so everything has to be in measures of radians here. All right, so we can get the angular speed. So 45 revolutions per 1 minute. Now remember, every revolution around the circle is 2 pi radians, so we can then cross out or chop the revolutions here, and that'll give us 90 pi radians per 1 minute. And finishing up here, the 45 RPM record has an angular speed of 45 revolutions per minute. There's answering the question now. So the angular speed of the record, if we just take r times that angular speed there, 1.5 inches is the radius times this, we'll get about 135 pi inches per minute. And that's what they wanted the answer in on this one as well. So approximately 424 inches per minute. So that's why I love trig, is because you can apply it to things we're going to learn as we go along. You can use it in real life and so forth. And in physics classes, you will find these formulas again. This concludes video 1.